Hi, everyone. Thanks, Pablo. Hi, everyone. It's awesome to be here. It's wonderful to see you all. And as he said, I got my PhD here at Harvard, so I'm quite honored and humbled to be here presenting to you today. And so it's very exciting. Really quickly, I'm curious about the audience. So raise your hand if you're a prospective student. Okay, I've got a group here. How about existing students, postdocs, graduate students? Okay. And then public, people who are not directly, awesome. Thank you for coming. And then the other set of questions I want to know, who's actually doing data science or analytics or computational work right now? Good portion, okay, scary. And who's interested in looking in that direction for your career or for future work or wanting to know kind of where that's going? Okay, so a great mix. My talk today is not going to be super technical. We can talk after if we want to get down to brass tacks about some of the more technical stuff. But my thought here today is to really talk about my experience as a data scientist and what's happening in artificial intelligence and analytics today, and what I'm excited about. And then finally, to share with you some work that I'm really proud of that I think will inspire you in your analytics and AI efforts. So again, thank you so much for having me. The only other thing to mention, Scientist Bob is my Twitter handle. It's always good to do a little marketing. Oh, I may need to plug this in. The Intel guy needs a little help with his computer. All right. Ta-da. Okay. So you've heard some of this before, but I'm just going to tell you a little bit about my journey to becoming a data scientist, because I certainly didn't start out planning to be a data scientist back in the early 80s. In fact, I only found out I was a data scientist a few years ago when it was published that data science is the sexiest job of the 21st century. And I said, thank you very much to Forbes or whoever it was that published that. So early on, I got my PhD in physics from Berkeley. I then came here in the physics department and did an astrophysics thesis with the very illustrious George Field. Spent most of my time at the Center for Astrophysics up on Garden Street. And my work was about computational models of stuff falling into supermassive black holes. So I was interested in figuring out how to use computers to solve problems in astrophysics. Obviously, that field has just exploded and has far surpassed anything I did. As a postdoc, I got interested in artificial neural networks, which were the early version of what we now call deep learning, and was early AI, or at least middle period AI. And so at that time, I did some academic work on neural nets and published a book, or co-wrote a book on time series forecasting with neural networks that ended up resulting in people calling me. So all of you postdocs, imagine yourselves at your desk. And imagine someone calling you out of the blue and saying, hi, I read what you published, and I want to know if you can forecast. What did they want to know if I could forecast? Stock market, exactly. So in 1991, I wasn't even sure what the stock market was, to be honest. But this is what they were asking me. So I said, oh, okay, well, this is interesting. There's a little bit more market demand for this forecasting thing than there was for models of black holes. So you follow the market trends. One little anecdote before I move on to the rest of the story, and my idea here is just to kind of give you a feel for the breadth of what you can do in analytics. At the time I was a postdoc and I was doing this neural network research, I got a new office mate, and he was an undergrad who had just graduated, and he was going to be coming to Harvard to work on his PhD. So they gave him to me as my office mate. And he was a great guy. We got along really well. We played soccer together and hung out. But every day, and I hope he doesn't get mad at me for telling the story at Harvard, but every day he'd come into the office. I hate my project. And I ignored him for about 2 weeks. And then finally I said, all right, what's wrong with the project? Well, I have to look at these sky survey images, and I have to circle the items that are interesting to my boss, and then write down their coordinates all day long. So imagine you're looking at an image with speckles on it, and you write down the coordinates of the interesting speckles all summer. Okay, so you can all understand why he was unhappy with his project, and I'm sure it was in the service of incredibly important work, but from his perspective, it sucked. So I said, well, you're just doing the same thing over and over. Can't we train a neural network to do your work for you? And he had worked for 2 weeks, so we had training data. So we did just that. We trained a neural network, and once it was written, and these things, in the 90s, these things took a long time to train, but once we got it trained, it ripped through his entire summer's work in 8 hours. Done. And he was just so happy. Happiest guy in the world. So we wrote a paper, and of course, being the senior guy, a very senior postdoc, I was the first author. He was the second author. It was his first academic paper ever. So again, he was very excited. This was great. So we kind of went off and did our own separate ways. And just a few years ago, his name popped up on the internet. And he had just won the Nobel Prize in Physics. It was our very good friend Adam Rees. And so I like to say that AI was impacting the world even back in the 90s. We just didn't know it yet. And in fact, historically what happened is there was an AI winter in which AI work sort of came to a halt because we didn't have the computing capability to train the models we needed to train. We didn't really have access to the amount of data you needed to create realistic AI models. And then also there were a few algorithmic improvements that needed to happen before we could really get these things right. So anyway, the AI winter happened, and now it's thawed. I'm happy to report, and it had a significant effect on the future of physics. So as you can guess, this is the result of those phone calls to ask me if I could forecast the stock market. I found out that someone I knew had a trading firm in Chicago. We formed a new company, and I ended up running or co-running with him a futures trading hedge fund for 12 years. And that was really where my love and appreciation for working with data was really hatched, because that was purely data-driven, very, very compelling, and it worked out well as a business as well. In 2006, as Pablo said, I switched into healthcare as product manager for the Humphrey Field Analyzer. Does anyone recognize that device at all? That's good, because it's the diagnostic device for glaucoma care. So I'm glad to hear that none of you are currently under care for glaucoma. And it was an interesting experience, because this was a product with 25 years of history, but no analytics whatsoever. They had done nothing with ongoing data. So we were actually able to create the ability to predict how fast a patient's vision was declining, and use that to titrate medication and other aspects of their care. So it was a pretty nice experience around data. And then finally, in 2009, the US government started incentivizing doctors to use electronic health records. The idea was, and this part's important for later on in the talk. The idea was, if you make healthcare data electronic, then we can use it to optimize care, we can use it to optimize care delivery, and you can actually improve our ailing health system. So we started this company, Apixio, with the idea that we were going to take the data from all these individual silos of healthcare data, pull it up to the cloud, and make it, map it so that it could be computed upon for optimization purposes. In other words, your data, if you see 10 different doctors, there are 10 different databases that have your information in them. They don't talk to each other, and that's for reasons of not just connectivity, but actually because semantically, the information is not represented in the same way. That is, a code in one health system for diabetes would show up as a different code in a different health system. So we had to kind of connect that information together. So we built that system. It was a big data stack, and what I'll show you in the next part of the talk is that it turned out that being able to include unstructured data was critical to that effort. So I'll leave it at that for now. And then finally, 2.5 years, as a result of a collaboration with Intel when I was at Apixio, I ended up joining Intel, where I've had a very good time doing what I do. So I could see when I stood up here and was introduced as chief data scientist that little question mark bubbles were floating over your heads. And the question that formed in your minds was, I thought Intel was a hardware company. Don't you just make chips? Why do you have a chief data scientist? Raise your hand if you were thinking that. All right, good for you. Okay, so you are absolutely correct. It's a good question, and the answer is that at Intel we've put a huge amount of effort and investment into creating capabilities in our hardware that can help accelerate or otherwise improve the computing experience. And the challenge is that people don't know about these capabilities. So one of the roles that I have is to understand what everyone out in the real world is trying to do and map what Intel hardware can do to what they're trying to do. So a really simple example, you can actually encrypt data on the fly with the hardware with almost no computing overhead. So you can have nice, secure, end-to-end encryption of data almost completely through the hardware. Well, hardly anybody knows that. So, and in fact, at Apixio, we built an entire encryption software stack to keep our data protected, and then later found out we could have used this Intel technology. So that's one component. The other component is that if, and this is more self-serving, if people succeed with their analytics objectives, whether you're industry or research or even individuals, if you can do the computing that you want to do and achieve those objectives, you tend to invest more in your computing infrastructure. So there's also value to Intel to just lift all boats by making it easier for you to solve the problems you need to solve. And and then finally, the other thing is Intel needs to have a forward-looking view of what to build next. And so when I work with folks outside of Intel on the challenging problems that they have, and that's particularly applicable to research groups like you have here, and I had some really super interesting conversations this morning that we might be able to touch on later, that if I can bring those forward-looking problems into Intel, it helps us design the next generation of chips to be more effective for what you're trying to do. So it's a nice cycle. If you kind of go meta on the whole, why does Intel care about data science, it really boils down to this picture right here. So this is what is floating around in our CEO's head. He loves drones. He loves his autonomous BMW. And he's very interested in problems that, that you can solve in various industries, but healthcare being one of the more interesting industries that's front and center for us. So all of these applications of computing have a hardware component. There are sensors and chips and CPUs and various other things happening in here from a hardware perspective. But to make them all work requires a very robust software ecosystem that allows you to actually put together these very, very complex sets of solutions. So at the end of the day, I think I was hired more or less because of this overall thought process, which is, this is a quote from our CEO: "Data is the new oil, and we're a data company." And so I think Intel is on a journey of becoming more and more of a data company, and you know, I was brought in as part of that journey. Now, what value can I bring? I don't know if you all recognize this very nebulous graph. No axes. I would have gotten a very poor grade on this in a lab course. But this is time, and this is mega amounts of information. Okay, so it's a graph that IDC put out in an analyst report about the explosion of data that's coming. And there is an explosion of data. But that alone is not necessarily a reason to be happy and excited. Here's another graph, also a little bit nebulous. At least it has its x-axis, so here's some years. And here's something that's increasing in time, but with a pretty big hockey stick. Anyone want to guess what that is a graph of? People, that's a good one. Yeah, it's highly correlated with that. It's the mass of the landfill. So hockey stick growth in some stuff is not necessarily valuable. So when we look at the growth in data, I think it's actually worth thinking about that analogy. The way to get value from that data is through good data science and analytics. And so the role that I play and that the role that we play as experts in computing is to really be able to take this growth of stuff and separate out the noise and pull out the valuable part. I think there's actually a fair analogy when our CEO, BK, says data is the new oil. It also implies that there's some refining that has to be done, right? You don't pour oil straight in your gas tank. You actually have to bring in a pretty complex process to convert it into something valuable. So I think that's an important part of why Intel needs a chief data scientist. I already talked about this. I think I jumped ahead of myself. But at the end of the day, what am I really about? I'm helping end users succeed with their analytics goals. I'm about helping partners use the technology that's available to the best possible outcome. So the encryption example that I gave, sometimes it's just about optimizing performance for different applications. If you have code that's written well, it actually performs, sometimes tens or hundreds of times better than code that's not written well. So we're always working on this, and then of course I'm always bringing those use cases back into the design process at Intel. At this point, I wanted to just talk a little bit, because we've got prospective students here. I wanted to talk a little bit about this part, which involves a team of architects and data scientists that I have that work for me and actually engage directly with end users in industry and research. And so the question that was put to me was, well, what do you look for in a data scientist when you are hiring? And I think when I think about a great data scientist, I start with the definition of data scientist and how I would contrast an analyst from days of yore, in other words, 3 or more years ago, and data scientists now. Analysts are really querying data and creating reports to the exact specifications of some business owner or manager who's told them, okay, I need a report on the number of widgets we sold last quarter, or I need a report on the amount of, the massive landfill within this geographical region. It's a very directed activity and very specific to creating reports. Data science is actually a conversation between the users of the analytics and the data and the technology that's needed to create those analytics. So a great data scientist understands the limitations of algorithms and understands, at least intuitively, statistics, but can also communicate with the stakeholders who are going to use those results. So the business, in my world, a lot of times it's a business unit leader working with a data scientist to figure out, well, what could we do? We can't just say we're going to make a data lake and hope that the insights bubble to the surface. Has anyone ever heard people talking about data lakes? Yeah. Data lakes can be great, but if you start with the data lake, you actually end up in deep water. And so the best data scientists are actually the ones who can really have that conversation, convert the goals of the organization into very specific questions, which can then be answered by a combination of the algorithms and the data. So when I look for data scientists, I'm looking for people who, sure, they have experience with the algorithms, but they can communicate amongst different stakeholders. I think the other thing, if you want to just be really, really tactical, is that you have to have experience with some really icky, messy data. It doesn't have to be a lot, but go do a Kaggle or pull down a couple data sets and just tinker with them. Because if you don't have experience with real data, you tend to make mistakes and you oversimplify things. Okay, so that's it. I'm sure Intel is always hiring, especially when I'm at Harvard. Intel's always hiring when we're at Harvard. So what's the, from my perspective, what's the value of doing AI or analytics? What is it that we're really able to get to? And I think I'm saying this in the context of all the background that we're hearing in our culture about AI is risky, AI is dangerous, AI is going to take away jobs. We have to watch out for AI. And all of those things are questions that we need to look at carefully and pay attention to. But there's also a lot of benefit that we get from AI. So what are the things that I see? When I think about AI, I think about ways of augmenting what humans can do. And the first thing is helping humans access information effectively. Another major value of AI is that it can reduce complexity. So AI can be used to take highly complex relationships, usually in some pretty high-dimensional space. That is, there's lots of variables at play, and can render it down to something that a human can kind of get their head wrapped around quickly and make a decision. So I think that's very, very valuable. And then finally, AI can just help with scale. So the most obvious example of that is internet search. There's just no way we could ever ingest all the content of the internet, yet a search engine can bring up pages that are highly relevant. And if we click on something lower than the top result, the search engine pays attention to that and tries to figure out how to improve itself for the next time around. So there's an AI machine learning component of that, and it renders an ability to handle scale that we just otherwise wouldn't have. All right, so I'm going to give you an example from Apixio, because this is near and dear to my heart, and I think it will exemplify the opportunity here. This is around access to information. So one question, raise your hand if you think doctors would make bad decisions if they had access to all the relevant information. Yeah, nobody thinks that. Maybe a couple, but generally speaking, if they had everything that they needed, they probably would make good decisions most of the time. In practice, healthcare providers are very challenged with access to information. So at Apixio, we took all the data from all the different sources across a health system, and we integrated them together. All the structured data, so all the problems, all the labs, all the meds, we put it all together into a single unified view. And we figured we had just cracked the nut on the healthcare problem. Multi-trillion-dollar a year healthcare catastrophe in America averted by Apixio, right? We can all cheer. So we brought all this data together and we looked at the problem list. The problem list is your diagnoses. And we said for all patients who have a key clinical condition that your doctor always needs to know about. So history of a heart attack, history of a deep vein thrombosis, brain bleeds, hepatitis. These are things that always affect your care. Every minute, every time, no matter how long ago they happened. We looked to see how frequently they were missing from the structured data in the problem list. So here's your chance to be as optimistic or as pessimistic as you'd like. Raise your hand if you think 0 to 25% of the data was missing from the problem list when we aggregated everything together. Okay, we got an optimist. You're hired. What about 25 to 50%? Sounds more plausible. Since I'm talking about it, it must have been kind of a problem. So maybe a third of the audience. 50 to 75%? Ooh, okay. Another, a little more than a third. What about 75 to 100? Ah, yes, we have some doctors in the house. Doctors always say 80% or more. They don't trust the coded data at all. Very interesting. So the answer that we got when we did our study, 63% or more. So 63% of the time, the coded data that computer systems are using to make clinical decision support decisions for your care don't know about something important in your care, if you happen to have that in your history. That's pretty scary. And for a startup that was going to base its entire saving the world on this aggregated data, pretty disappointing. The good news was we discovered that the information is in the text. So when doctors dictate and when they type, when they send each other letters, like a consultation letter or a discharge summary from the hospital, huge amounts of information are there. And I'll just give you an example of how this worked out. This is actually the aggregated problem list for a real patient who's been de-identified. The doctor's notes, this is the primary care doctor, did have written down hypertension as a diagnosis for this patient. And hypertension is not mentioned anywhere in this aggregated problem list. And then the smoking gun, this is actually a scanned letter from the patient's cardiologist that was scanned into the primary care doctor's electronic health record. And it says, I think very ironically, you are aware of his coronary heart disease, acute myocardial infarction, which is a heart attack, 4 years ago, da-da-da-da-da. So the cardiologist actually even ironically says that the patient has had a heart attack, but it's not coded anywhere in the patient's coded history. So that's a major concern. So it ends up that the trick to doing analytics in healthcare is to be able to use unstructured data. And by unstructured data, I mean the clinical text, as I was describing, images, image reports, video, audio, traces from EKGs. You have to be able to analyze all that data and bring it into context. And the way you bring it into context is to use machine learning, where you can, first of all, extract features from the text or the images using AI capabilities, and then use machine learning to actually compute whether or not you're confident that a particular diagnosis is real or that you're missing a diagnosis. Now, okay, so this is the part I wanted to just define, since we've got a broad audience, I wanted to define what I mean by machine learning and analytics and AI. So this section I call reports, regressions, and rabbits. This is the report part. We did another study at Apixio where we looked at major conditions. This is before we realized the text was going to save our lives. We said, okay, well, maybe there's stuff missing, but at least if there's a major condition like heart failure, you'd expect that it would be real. I mean, if you have heart failure, you have a 5-year life expectancy. You're in and out of the hospital. You're one of the most expensive patients, and you're also one of the most fragile patients out there. So hey, if you got heart failure on your problem list, that's pretty serious. It must be real, right? So that's the report. Good old analytics. You do a query in the database. You ask how many patients have heart failure. This is the answer you get. Turns out we did a deeper study of those patients, and when we looked at the ones that had heart failure coded for them, only about 70% had heart failure. The other 30% didn't have heart failure. Many of them didn't even have a cardiac condition at all. They had been coded for heart failure because in order to get something paid for, it was convenient to put heart failure as a diagnosis. Wow. So a little scary. We're all going, oh man, I better take some vitamins today. So how can you address this with machine learning? So what you can do, and this is a cartoon model. Please don't go home and write any papers on this. Ejection fraction is something you can measure with an echocardiogram. It tells you how well your heart is pumping blood into your vascular system. Edema is swelling of your ankles, and these are 2 symptoms of heart failure. So it's not totally crazy. And so what we can do is take our 10 patients that we had on our previous graph, and we now map them out this way. Each patient has a value for the ejection fraction and edema. And then we label the patients according to whether they actually do indeed have heart failure or not. And amazingly, in this graph, there's a perfect straight line that goes right through the data, dividing the world into heart failure and not heart failure. Obviously, slightly cooked up. This is the regression part. This is what's known as a logistic regression. It's just a classifier that draws a straight line on your graph. And so you're all thinking, oh, well, machine learning's easy. This is lame. I learned how to do this in high school. And you're right. It's very, very simple. Machine learning is simple. But what's cool about it is that instead of 2 variables that you're connecting to create this division, you're actually looking at anywhere from thousands to millions, depending on how you organize your data. And so we can go through the typically tens of thousands of parameters and figure out where to divide up the space so that you get meaningful divisions of heart failure and non-heart failure patients using machine learning. So that's pretty amazing. So machine learning is really allowing us to handle very complex data in high dimensions. It's very hard for us to picture or to put on a piece of paper. So I'm going to pause here. This is where we start talking about deep learning. So I've talked about reports and traditional descriptive statistics and analytics. And I'm going to paint a picture of the landscape of analytics that kind of goes in a continuum from that those descriptive techniques, the reports, through modeling and machine learning, which is my regression section, and I'm going to get all the way to AI. So one way to think about that distribution or that spectrum is about what kinds of questions your methods can answer. So when I'm doing reporting, I can ask questions like, oh, how many widgets did we sell last quarter? Or how many heart failure patients are in the database? And I can get a report on that. And so that's kind of where I am. Now, if I want to ask a more complicated question like, well, what do we expect our sales of widgets to be next quarter, then that requires a different set of tools. And that's moving us a little bit more into the modeling, machine learning, statistical methods realm. The next set of questions says, well, what do we expect to happen next? That's really where we're getting into machine learning, or what are the causative factors for what we're observing? So machine learning algorithms really start to help us there. So raise your hand if you've heard about deep learning. Good, everybody pretty much. Deep learning is the set of technologies that has really exploded the AI world. And what deep learning has done that's fundamentally different is it's allowed us to ask questions about unstructured data. So all my previous examples were on data that can be put neatly in rows and columns in a database. No offense to our researchers here on NoSQL databases. But you know, your structured data fits in a nice rectangular set of rows and columns. What deep learning does is it allows you to actually ask questions of text, video, images, audio, information that's not already been rendered into a simple granular form. So this is just an example. Intel recently acquired a company called Nirvana. They're experts in deep learning. And this is just one of their little things. They have a deep learning system that can recognize what sport is being depicted in video. So with a 0.99 something, don't know what that number is, but we're going to assume it has something to do with confidence. This is diving. Seems like a pretty good guess. So the question is, and I'm being very specific here, what sport is being depicted in the video? Okay, it's not answering any other question about the video. So that's where we are right now in terms of our technology. Where is AI going, and where do we anticipate it to get soon? It's in understanding context. So quickly, think of the image that came to mind when you saw this word. Okay, now raise your hand. Raise your hand if you thought of a little laptop thing like this. All right, a lot of people. Raise your hand if you didn't think of that. Putting you on the spot. What did you think of?
A drug.
A drug. Okay, raise your hand if you thought of a drug. Okay, so smaller number here. We are more technical and less medical in this room. Some audiences, it actually flips the other way around, which is pretty funny. Did anybody not think of either of those things? Yeah? Codiform tablets, exact. Like stone tablets that, exactly. Moses. Right. So depending on what the context is of my talk and my audience, and really where you are in your thought process, you're going to have a different interpretation. So if I ask an algorithm, what's the answer to this? It depends on context. So an AI algorithm that is kind of hitting where we really think AI needs to go, it's actually able to create that context and, in fact, adapt. Because if you think about it, those of you who raised your hand when I said one of these computer thingies, what do you think would happen if you were in a hospital trying to get a nurse's attention? What would be the most likely interpretation? It would probably be the medical one. And I'll leave it to your imagination what the context would be for the stone tablets. Okay, so now we're to the rabbits portion of the test. So we finally got to rabbits. So again, if I asked you the question, what's the answer? You'd say, what are you talking about? I mean, you might be tempted to say rabbit, but then I'd say, no, that's not the answer. This is a Holland lop. Actually, I'm lying. It's not a Holland lop. I don't know what kind of rabbit it is. But there's a lot of questions that one might ask about this depending on what you're trying to get to. So the place where there's a lot of research and effort in AI right now, and where we're not quite there, but it's tantalizingly close, is in building in this context. And you can imagine how important that is, because when you get a reminder to stop and pick up your dry cleaning from your phone, and you're racing to the ER, that's extremely annoying. And so context is important in the application of all these technologies. Okay, so I've got to save myself time for the last thing. So I'm gonna go through what's coming in AI quickly. There's infinite amounts of things to talk about here. But the things that are hitting my radar, transfer learning. Transfer learning is the idea that you can take a deep learning or AI model that learned one problem. So for example, I can recognize rabbits, cats, dogs, trees, and motorcycles, and then tweak it or customize it to solve another problem. So I have widgets coming down an assembly line, and I want to be able to recognize them, but I don't have millions of examples of bad widgets. I have a few examples. How can I train a system to recognize bad widgets quickly based on the fact that I have this other system that recognizes rabbits, cats, and trees? Well, that's transfer learning. It turns out for certain domains, it's very, very powerful. For images, very powerful. I was just having an interesting discussion this morning. For text, right now, we don't have mature techniques for transfer learning. But you can imagine how valuable it is to be able to take one set of capabilities and quickly adapt them to a new customized problem that you have. So I'm really excited about transfer learning. Simulated data. Who here has heard of AlphaGo? Okay, so most everybody. AlphaGo and AlphaGo Zero are the systems that beat the world-class, the top world players in the game of Go. The most recent one was trained without any human input at all. Basically, they took two systems and they had them battle each other, trying out different strategies, simulating the game, and then recording which strategies work better, and then just keeping battling the best one, the latest best strategies against new experimental strategies. They ended up with something that can beat the original AlphaGo 100 times to nothing. So simulated data is this idea that you can create the data you need to train AI systems through simulation without having to actually do it in real time. That's really helpful when you're building an autonomous vehicle and you don't want to train it by crashing it into walls, right? Do it in simulation. And in fact, they've done this with Grand Theft Auto. I don't think I'm going to get in trouble for promoting a product. You can actually train an autonomous driving system by having it watch a human play Grand Theft Auto. And it gets pretty good performance. So that's all in the simulation world. I think that's pretty amazing. What's that? Oh.
He said that's how he learned to drive.
Yes. Yeah, I could have benefited from simulated training myself, believe me. And actually, I'm going to throw out some props. My 4 sons and my very good close family friend are in the audience, and they remarkably have done very well with their, they haven't needed simulated driving. So thanks for coming, and thanks for not crashing any cars. We have imitation learning. So if I want to teach a robot to do the dishes in my house, I put on my AR, my VR, and I do the dishes. And then the robot learns to customize. Again, it's an application of transfer learning, but it's a very specific one for creating strategies for doing series of tasks. That's growing a lot, and it's very important. And then finally, self-explaining analytics, another topic that I actually talked to several people this morning here at Harvard about, that algorithms that just give you an answer aren't sufficient. You have to know why, or you have to have some direction about what do I do differently to get a better outcome. So that's a small sampling, but they're all really interesting. They're interesting from an algorithm and data point of view. They're interesting from a hardware point of view. So love to talk about those. And now finally, I'm going to tell you why it's amazing to be chief data scientist at Intel and why it's great to get up every morning. Intel has funded me and allowed me to co-lead a program at Intel called Intel Inside, Safer Children Outside. And so I and 2 other executives work with the National Center for Missing and Exploited Children, which is the national clearinghouse for information on missing children, child pornography, and online sexual exploitation of children. We're also working with Thorn, which, name drop alert, this is Ashton Kutcher's private foundation that is dedicated to fighting online, or eradicating, let me get it right. They're dedicated to eradicating child exploitation material from the internet. So it's interesting because it's not exactly the same mission, but they're very overlapping. So one of the problems that we've solved or worked on with Safer Children is that there are 2 to 5 million new online ads in the US every year selling a child for sex. So think about that, 2 million online ads being created. Law enforcement has tools, courtesy of Thorn, to recognize when a child is in one of these ads. But then they have the challenge that they'd like to know, is it a missing child? Well, the National Center for Missing and Exploited Children has a database of 40,000 images of missing children. So the task is to match up the image in the ad with an image in a database of 40,000 images. And what they do right now is they actually do that by hand. So let's try that. I'm going to go to, hopefully I could have loaded this ahead of time, but it worked. This is amazing. Okay, we're going to try that. Now, this is not scary. These are child actors. We don't have any children at risk here, depending on how you feel about stage parents. We're going to look for the kid. We're going to look for the kid on the left in the database on the right. So that's the answer for this one. Let me shrink this down a little bit. All right. So we're going to start. We're looking for this child actor in this database of 10 images. So let me know when you see the kid. Top left, right. Okay, got it. Now we're looking for this kid in this database of 50 images. So again, let me know when you see the kid. Yep. Now, what's interesting about this is actually running on Amazon, and we're randomly pulling the data each time. So I actually don't know the answers to these. Okay, that looks like Miranda Cosgrove. So we're going to look for Miranda in this database of 100 images. Let me know when you see the match. Okay, there we go. All right, so we did it. That was a pretty easy round of manual search, but you can imagine searching 40,000 images. It's pretty much impossible. The folks at the National Center actually have memorized a terrifying number of those images and do find matches, but it's pretty rough. So what we did in our work with Thorn is we created an AI system with a very specific question in mind. And this is getting back to that problem of defining the question really carefully. So the question was, if I show you 2 images, can you tell me, yes, it's the same kid, or no, it's not the same kid? And it doesn't matter how many years between the pictures. It doesn't matter if they changed their hairdo. It doesn't matter if they're wearing different clothes or if they're wearing makeup. So very specific. It's not a generic facial recognition problem. We actually were much more specific, and I think that's a really important point about this. And then we said, take that algorithm and just sort the 40,000 image database based on how likely it is to be a match. So let's see how easy it is now. And this is running in real time, by the way. This is actually pulling these images, running the AI, and sorting them in real time. So it says it's that girl. Lo and behold. This kid, it's putting this kid first. Okay? And then finally this one, and the AI pulled up this kid. Done. That's it. So we've taken an impossible task because of the scale of the database, the actual scale of the problem, and we've made it not only possible, but actually quite easy for the analysts at the National Center. And so we're actually deploying this in the next month at Thorne, and presumably, fingers crossed, this is going to have a huge impact on their ability to match up the children who are actually reported missing and are being trafficked with the children who are showing up in these ads. I am extremely, extremely proud of that, and I think it's a really fantastic example of what AI can do in terms of augmenting humans as opposed to replacing humans. Now, I'm not going to be Pollyanna-ish about it. There are real challenges around AI that we need to pay attention to. You know, is the AI autonomous vehicle going to run over a cat, or is it going to run over grandma when given the choice? Well, these are important questions. Although I think the reason I bring up that example is because we often see these questions being framed in the wrong way. So it's very important to have an open dialogue with practitioners and regulators. I've been having some really interesting conversations with the FDA and with lawmakers, asking me what's my opinion about how do you regulate these things. There's definitely real issues that we need to pay attention to, but transparency and an understanding among the public about what AI is and what AI isn't, I think is critical to that conversation. So everyone in this room is an important participant in that process. And I think we're going to see some shifts in jobs, but what I've seen so far is some really amazing opportunities to help people do their job better, faster, and smarter, rather than simply replacing them. So I think there's some real benefits to go along with the challenges. At the end of the day, access to information, reduce complexity, and scale give us some real power at our fingertips through the magic of analytics and AI. So thank you very much, and it's been wonderful to be here. Oh, we have time for questions. Okay. Anyone have questions? Okay, I think I saw one here. I was looking this way first, sorry. Yeah, self-explaining analytics. So one of the areas where deep learning especially is quite challenged is the way deep learning systems work is they're, regardless of how they're architected in terms of how many layers and how many feedback loops, at the end of the day, the really amazing thing about deep learning systems is that they learn a set of features about the data directly from the data. So the benefit of that is in our AI example here with the missing kids, and I think this is really a fundamental sea change in analytics. You can program deep learning systems simply by giving them examples. So pairs that are the same kid at different ages are yeses, and everything else is no's. You put the images in a folder. You let the algorithm go to town, and at the end of the day, if you're lucky, you end up with an algorithm that does your task very well. It figured out what's interesting about faces and about faces over time without you explicitly telling it. The challenge, though, is that you don't know what it did. You don't know why it made that decision. So, if you're doing an algorithm for healthcare where you're recommending a particular treatment or diagnosis, it's going to be very hard for a doctor to take that advice without input. So the trick is, how do you interrogate these systems to understand what's important in the decision-making process? And there are a few strategies for this. It's definitely something where I'd say we're only a few % of the way into the discovery of all these techniques. Traditional machine learning methods quite often do have some direct way of exposing the reasoning. For example, if we go back to our amazing, Okay, so our amazing regression here, we can literally see that if a patient was called out as no heart failure, it's probably because they had a, see, this is no heart failure, so they had a high ejection fraction and a low edema. And you can kind of see at each point how important for this location, you can kind of figure out how much ejection fraction would impact your decision making given a particular edema, for instance. And even in higher dimensions, you can do that pretty well. You can kind of see how much each variable impacts your decision. But in a lot of cases, and especially deep learning, that's not possible. So we're doing a lot, or at least we're seeing a lot of research right now on algorithms or methods to interrogate those systems to understand why they make those decisions. So for instance, you can feed them different types of data and then see which parts of the system light up. It's almost like doing MRI imaging of like functional MRI of the brain. It's a very similar kind of thing. But the nice thing is you can probe the values of all the different parts. I've seen some methods where you actually use deep learning systems to interpret the activations inside other deep learning systems. So the other thing you can do is you can actually start with a particular place in a particular parameter, a set of inputs, and look at the behavior of the outputs of that deep learning system near that point and create sort of a local approximation that gives you some idea of what values it's sensitive to. That's pretty hard to do in practice. So it's really quite new. And in fact, we've got some hardcore research going on around that work right now here at Harvard. So it's an exciting ongoing process. But at the end of the day, I'll give you an example. And this is also an insight into my brain. I was looking at Twitter data, trying to figure out what caused some tweets to get a lot of activity, follow-back activity and engagement, and what what didn't. And so, with a deep learning algorithm, you can train an algorithm and it will tell you, oh, this tweet should get high engagement. Well, then you say, well, why? Because I want to create the next tweet to follow that pattern, and that's not so easy to get to. So that's kind of what I mean by self-explaining algorithms. And I think there's a huge amount of opportunity around that in terms of creating ways to do that. Yes, questions? Yeah. Yeah. Well, so I have to say that the models that we used were very statistical based at the end of the day. But yeah, it was very successful. We had good returns for 12 years, and it was purely forecasting the S&P 500 futures out a few hours at a time, and just purely based on statistical models of how different. The way to think about it conceptually is, suppose someone's throwing rocks into a pond, and you're observing the pond, but you can't observe the person throwing the rocks. you can't predict exactly where a rock's going to land in the pond, but once a rock does hit the pond, you can estimate from the initial splash what the impact's going to be. And if there's multiple rocks happening, you can kind of predict what the waveforms are going to be. That's kind of what we did with our futures modeling, and it worked well. I will tell you that eventually it stopped working, which is why I changed fields. And I, got out while the getting was good, luckily. Early on we had, so this is 1992, we had good algorithms and a 7-foot tall guy in the futures pit filling our orders, right next to Goldman Sachs. And that was an amazing advantage because we had great liquidity, we could execute our trades really easily. We were one step ahead of the curve. By 2006, the futures pit looked like that back corner of the room. It was empty. There was like 2 people in there. And so our 7-foot tall guy was no longer that relevant. What was more important was actually how long was the fiber optic between you and the server in the exchange. And so that was a different game that I wasn't really that interested in playing. And of course, at the same time, I wasn't the only person in the world who thought, oh, let's use modeling to predict the futures. So the competition was increasing at the same time. So it was just a natural time to move into something that felt more human. Yeah, sorry, go ahead.
When does big data analytics transition into AI?
When does big data analytics transition into AI? That's a great question. So there's, so I guess what's the best way to put that? I mean, the way I think about big data analytics is it's really in some ways methods for handling huge amounts of data at scale. And so from that point of view, they're sort of complementary, right? You can do big data analytics to just develop statistical models or simple machine learning or AI. So I think it used to be, I would say a couple of years ago, people would have said, when you have millions of labeled examples in your big data, then you can start to think about creating AI. I mean, if you look at the vision systems that are out there today that have started to surpass humans at specific tasks, they're trained on tens of millions of labeled data points. What's interesting is, well, 2 things have changed. One is you can, and that training was generally done on a single sort of super highly optimized single node system, like a single computer. Now, you actually can do deep learning on the same infrastructure that you do big data analytics. In fact, Intel just put out a library called BigDL. I'm so glad I get a chance to talk about this, because I'm very excited about it. This BigDL allows you to do deep learning training on scale-out systems, specifically Spark. So you can all of a sudden do deep learning training with the big data infrastructure that you have without any moving data or translation. That's actually very cool. The other thing, though, that is transfer learning. Transfer learning has really changed the game because now you can do AI with much smaller data sets if you've got a trained algorithm. So I sort of think of them as, sort of, I don't know, parts of a complementary spectrum of some kind. One last question. I think he was waiting for a while.
Yeah,
Sorry.
What's Intel doing to speed up the tensor or matrix processing?
Fantastic question. What's Intel doing to speed up the various kind of processing for instance, deep learning and AI training? So let's see if I can go back. So this kind of falls into, where am I here? Come on. Here we go. All right, so it's this column here. Intel is, I think, the 3rd largest software company in the world, even though we don't sell any software. So what are all those software developers doing? They are experts in making other people's applications perform really, really well on Intel hardware. So we have a couple of very large teams that are actually optimizing so the question was really about what is Intel doing to optimize the various frameworks for AI. So there are a bunch of different software frameworks that you can use to develop AI, things like TensorFlow, which was created by Google, Caffe, Theano, et cetera, et cetera. There's a whole bunch of them, but TensorFlow is one of the big ones. So we've got teams of these experts. They have actually optimized for TensorFlow, Caffe, and some others, but they're hitting as many of these different AI frameworks as possible to make them run well on Intel. And in fact, the newest generation of Intel hardware, which is called, I think we call it Xeon Scalable, is actually very, very fast at doing deep learning training all on its own. But that's an ongoing process. The other part of the equation is when you need that super fast training performance for a very specific deep learning problem, we just recently announced something called the Neural Network Processor, which is an accelerator that is designed from the ground up to be accelerating deep learning training. And so that's pretty exciting because when that comes out, I think we're going to have some additional really cool ways to optimize for AI. So it's a mix of ecosystem optimization around all the different software pieces and also continuing to evolve our hardware roadmap to try to hit the bullseye. Good. All right. Well, thank you so much. I really appreciate the time. And thank you to my very kind hosts. I had a great morning, and they were wonderful to provide lunch. And so thank you, everyone. God bless.